In the previous video, we went through the different components that go into fluid and element kinematics. And we specifically talked about how a parcel of fluid moving from time at t naught to t plus delta t is the sum of the translation of the fluid, so the simple translation or movement of the fluid parcel from one position to the next with no change in shape. The linear deformation of the fluid parcel that has to do with the velocity at the different points being at different speeds, so spatial gradients in the flow. And so as the parcel moves from here to here, it might get longer because the part of the parcel is moving faster than the other part of the parcel. Then we talked about rotation, so we have that square fluid that might rotate like this or like this. And so although the shape's the same, it's actually at a different angle relative to our coordinate system. Okay? The one we left off was angular deformation. This is one that gets a little bit complicated, but has a huge importance when it comes to thinking about the dynamics of fluid flow. Okay, so I wanted to spend a little bit more time on that and see how we're going to use this definition of angular deformation to derive the idea of the vorticity of a fluid. Okay, so in angular deformation, what you have is that you might have the parcel at A here moving in the x direction at the velocity u and in the y direction at the velocity v. And then the points B and D, because they're spatial gradients in the flow, point B is going to be moving at v plus dv dx, and D is going to be moving at u plus du dy dy. And so D is moving faster than A, and B is moving faster than A vertically. Okay? So I actually drew this wrong. This should be pointing up. But you get the idea. So again, B is moving upward faster than A, and D is moving from left to right faster than A. And so what happens is at time t naught plus delta t, the position at A again is going to be u dt in the x direction and v dt in the y direction. But the point B is going to have moved up a little bit further, just like in linear deformation. It's going to have moved up at and it's spatially at a rate a little bit faster, so it's going to move a little bit further, and that distance that it's going to move relative to A is going to be dv over dx times dx dt. And that's going to be that distance here that you see. So this is this distance here. Okay? And so that's going to create a little bit of an angle. So it's that same phenomenon that happened in rotation. Now we have this d alpha here because there's an angle now between A and B. The same thing happens at D, but again, they're not necessarily moving at the same rate, and so they could be going opposite directions in this case, or they could be going the same direction, positive, negative, and they could compensate for each other. But the point is they're both moving basically towards C, and so D's moving at a fast rate, and so you've actually compressed that fluid parcel. Okay, and so now D has moved a little bit further than A, and that further distance is du, dy, dt, and that creates a change in the angle of d beta. So we have d alpha and d beta as our two angles we've now created with between A and D and A and B relative to the previous square fluid parcel we had. Okay, and so often what we want to know is how fast those angles are growing, or can we define another term? And so what we're going to do is define a term omega, which will ultimately, and we're going to call omega A, so omega A is going to be, AB is going to be defined as the limit as dt goes to 0 of d alpha dt. Okay, so we're going to define this rotation or this vorticity as the rate at which alpha is changing. And so it's going to be defined as the limit of dt of d alpha dt. Okay, well, as dt gets small, then d alpha presumably is going to get small. So as we make dt really small, and approach 0, then d alpha is going to be small. And so for small angles, we can say that the tangent of d alpha is equal to approximately d alpha. Okay? And that's, we've already defined, is going to equal dv over dx dx dt all over dx, right? So that's the change in the angle alpha. It's dv dx dx dt over dx. And so what we're doing here, again, is taking this component here, so this component here, and dividing it by dx, which is just this distance here, dx. Okay? So that gives us the definition, mathematical definition for d alpha, or the tangent of d alpha, and that simplifies the dx's cancel. So that cancels and that cancels. And we simply end up with d alpha is approximately dv over dx dt. Okay? And so if we take the limit of that term, so we have d alpha over dt, so now let's plug this into our above, so we say omega of AB is equal to the limit of d as dt approaches 0 of dv over dx dt over dt. And you can immediately see that the dt's cancel, and so the limit as dt approaches 0 is just dv dx. Okay? So that's for omega a b. We can also define for omega a d, and that is the limit as dt goes to 0 of du over dy dt over dt, which just goes to du dy. Okay? So now we have the definitions for this idea of vorticity, this rotation rate omega. So it's dv dx for AB, and it's du dy for AD. And so what we end up doing is to get the rotation around this particular axis. So when we have our square, we've defined this and this as omega AD and AB. What we really want to know is the rotation around this point here for the axis coming out of the board, and we're going to call that omega z. So we're going to say omega z, the rotation, omega z, is going to equal 1/2 of dv over dx minus du over dy, where positive is counterclockwise. Okay, so positive is going to be in this direction. It's going to be counterclockwise positive. And we can do the same thing for the other coordinate system, so we can define omega x is equal to 1/2 of dw dy minus dv over dz, and omega y is equal to 1/2 du over dz minus dw over dx. Okay? And those are what we call the vorticity, essentially. So this is the rotation rate. All right? And we can combine those, so we're going to combine all of these into one rotation vector. So we can, again, just like we did with velocity, we can say omega is equal to omega x I hat plus omega y j hat plus omega z k hat. And you should remember some of these terms from when we looked at conservation of angular momentum. Okay? formality is we're going to say that this is equal to 1/2 the curl of V, or equal to 1/2 our del operator cross V. So it's the cross product of the del operator and V. And so if we write that out more formally, that's going to be 1/2 del cross V, and that's equal to 1/2. And then we take the determinant of this matrix. We have I, J, and K hat in the first row. We have d over dx, d over dy, d over dz in the second row, and our velocities u, v, and w in the bottom row. And so we can take the determinant of that matrix and get our different vorticity components. And then we ultimately define the vorticity as 2 times omega. And that's where that half comes in. It really just comes into the way we want to define the rotation versus the vorticity. And it's for numerical convenience. And then again, that's just equal to del cross V. Okay? So for a particular axis, so if we think about omega z, a fluid parcel will only rotate around the axis. So if we have this fluid parcel like this, and if we say the z-axis is coming out this way, it will only rotate around that axis. So if we say omega z is equal to dv dx minus du over dy, okay? So omega z is equal to dv dx minus du dy. It will only rotate undeformed if, so it will only rotate undeformed if dv over dx is equal to negative du over dy. Okay? What that means is that the points all on the parcel are rotating at the same speed, so it will move. Otherwise, there will be rotation. So if they're not equal, if dv dx is not equal to negative du dy, then there will be rotation and angular deformation. And so you'll have that, not only will the parcel move, but it'll change shape as well. Okay? And then another situation, and what we've done for most of this class, is we said that the flow is irrotational. And then that's the case if du over dy is equal to dv over dx. There's no rotation, right? So if dv dx and du dy are equal, then omega z is equal to 0, and there's no rotation. Hence, we can also, you'll see this, del cross v is equal to 0. Okay, and you've seen that before in our assumptions of the Bernoulli principles. And this is what we're talking about. It's irrotation. There's no rotation in the flow. That assumption really greatly simplifies a lot of things when we do analysis of flow fields. And it's, again, an assumption we've basically made up until now in this class. We're not going to get into a lot of what happens once you have to add this vorticity. As you move forward in your study of engineering, you need to be aware of this is really where that assumption is coming in. And when we look at this differential analysis of fluid flow, we're going to have these terms are going to be present. We'll hopefully be able to get rid of them some, but this is where it comes in. And when we see flows that are turbulent and you see all the eddies and things, those flows are highly rotational, and del cross v is definitely not equal to 0, but at a larger scale, a lot of times we can make some of these assumptions. Okay, so that's vorticity and angular deformation. This is a little bit of a longer video, but again, a very important topic that we really haven't dealt with yet in this class.